So today we are going to discuss one very important topic called geometric dimensioning and tolerance. It is popularly known as GD and T. Now we have come to the end of the session. This will be the last lecture, and I will be covering two topics. Namely, I will be talking about geometrical dimensioning and tolerancing, and then I will also give an introduction about the concept called robust design. Robust design. Now let us see where we stand. We have started designing with the product. We have the detailed drawing of the product. Technically speaking, the embodiment design is over. So we have the detailed design, detailed drawing of the product or the solid model. At times we will have the drawing, at times we will have the solid model. So you have the drawing of the product in your hand. Now the question before us is, it can be released for production. The drawing can be released for production, then the components can be realized. You have taken the manufacturing difficulties into account, assembly difficulties into account in your design itself, so that you will be able to smoothly manufacture parts, assemble them together, and then realize the product. Now in all the, you already you know how to make drawings. You have made many drawings probably. Okay. So suppose I take a simple case of a shaft. I take a simple case of a shaft. I have a shaft here. Say the diameter of the shaft is you have the shaft, the diameter of the shaft. How will you specify? You will specify the diameter as say 30 mm. Let's not bother about other details. The shaft length and other details, let's not bother. Let's concentrate on what this feature alone. The diameter of the shaft is 30 mm. Now you release it for production. Say suppose, okay, let's give the length alone. Let me give the complete dimensions of this. Let me give the complete dimensions of this. This is say 100 mm. Okay, this is chamfer 1 into 45 degrees. Okay. So all the dimensions are given. So I have a shaft which is of length 100 mm, diameter is 30 mm. Is it okay? You have chamfers at both ends. Okay, chamfers, they eliminate the sharp edges and also they make your assembly job easier. So you have chamfers at the both ends and you have the drawing ready. Now my question is, can I release this for manufacturing? If I release this for manufacturing, will the manufacturing people, will they be able to make this component and then give it back to me? This is what we are studying, is it not? In the embodiment design, you should release the drawings. So to perform certain functions, I have designed a shaft. The dimensions of the shaft are finalized. Now my question is, can this be released for production? Is there anything missing here?
Performance, tolerance, discrepancy, acceptance, allowance.
Now, if I mean, all these answers are right. If I release it for production, my production manager will immediately send it back to me. The reasons are twofold. The first reason is, as far as an engineer is concerned, there is nothing called 30 mm diameter. It may sound very shocking. A diameter of the shaft Okay, I cannot make a diameter of a shaft. I cannot make a shaft which has diameter exactly 30 mm. Because the exact dimension 30 mm is something elusive. It doesn't exist in reality. What do you mean by a diameter being 30 mm? Is it 30? 0.000000000. Please remember, anything in between 20 and mathematically speaking, even mathematically speaking, anything between 29.5000 to 30.4999 is 30. Mathematically speaking, anything between 29.50000001 to 30.499999 is 30, is it not? So, to what dimension am I to make the shaft? Is it to 29.6? Is it to 29.7? The idea is, in engineering, a feature with a dot value. By dot value, what I mean is exactly some value. It doesn't exist. Are you able to appreciate this fact? Now, what is your height? Let's come back with some other example. What is your height?
185 centimeter.
185 centimeter. Okay. Suppose say he is not 185 centimeter, I am sure. Are you? Okay, fine. Good. You are 6 feet 2 inches. Good. Okay, so you have a 6 footer in the class. Good. So you have 185 centimeters. What do you mean? The height being 185 centimeters. Is it 185.00000 centimeters? Now if I measure it with, say, a height scale, in the physical education department, probably the accuracy of the scale is only 1 centimeter, the height is 185 centimeter. Okay, suppose if I have a laser height measuring device, which nowadays many even commercial establishments have, a laser height measuring device, which has a resolution of, say, 1 millimeter, with software compensation and all that. A 1 millimeter resolution. They use a very crude lasers. Okay. Then what is his height? His height will be 185 point, probably, I don't know, 3 centimeters. If I use a much more sophisticated equipment, his height is 185.34 centimeters. A much more sophisticated equipment, 184.343 centimeters. Goes on. Depending on the accuracy of the equipment, the height varies. The person is the same. Now all that I'm trying to convey is, there is nothing called exactly 30 mm. It doesn't exist. Even it doesn't exist. Forget about measuring. Exact 30 mm, does it exist? No, it doesn't exist. So, when I say the dimension is 30 mm, I should automatically specify the tolerance within which it should be 30. Do you understand? Whenever I specify a dimension, I should also specify the limits within which that dimension must lie. Why should I do this? Because there is nothing called, in engineering, there is nothing called a dot mm, an exact dimension. Exact 30 mm in engineering, it doesn't exist. It is something imaginary. Is it okay? Now the second thing is, whenever you ask him to manufacture, whenever you ask a person to manufacture something, He cannot manufacture anything to exactly 30 mm diameter. No one can manufacture. Any accurate machine cannot manufacture a product which measures exactly 30 mm. 30 mm doesn't exist in reality. Exact 30 mm dot doesn't exist in reality. Then where is the question of manufacturing? You understand? So, making something also requires a tolerance band. I can manufacture something, I can manufacture a diameter within say plus or minus 0.1 mm or plus or minus 0.01 mm. For example, all of you know about lathe. If I just make this diameter in lathe alone, I can maximum get plus or minus 0.1 mm accuracy. When you make it using a lathe, I can get maximum an accuracy of plus or minus 0.1. At the same time, when I do the same job in grinding machine, I can probably get an accuracy of plus or minus 0.01 mm. If I machine this in a grinding machine, I can get an accuracy of, there is something called a cylindrical grinder. In our own machine shop, we can see a cylindrical grinder. If I machine it using a cylindrical grinder, I can get an accuracy of 0.05 mm. So if I machine it in lathe, so I have a machine, I have an accuracy. If I machine it in lathe, I can get an accuracy of plus or minus 0.1 mm. If I machine it, say in cylindrical grinding, if I do it in cylindrical grinding, I can get an accuracy of plus or minus 0.1 mm. See, there is another machine called centerless grinding. If I machine the same component in centerless grinding, I can get an accuracy of plus or minus 0.02 mm. Now the basic question is, if I blindly say 30 mm, the production engineer doesn't know in what machine he must finish this particular component. In what machine he can machine this component. Whether it is to be machined in a lathe, or whether it is to be done in a cylindrical grinding, or whether it is to be done in a centerless grinding, he doesn't know. Probably, if I do some pouring or lapping, some other process, I can get an accuracy of plus or minus 1 micron. There is some other process called cylindrical honing or cylindrical lapping, in which case I can get an accuracy of 0.01 mm. This is 1 micron accuracy. Now the basic issue is in which machine to manufacture. That I will know only if the tolerance band is specified. So, it is not good enough if you just specify the dimension, but also in your drawing you must specify the tolerance band. So it is not good enough if you just say 30 mm, I should say 30 plus or minus 0.01. What is the meaning of this? The shaft will be accepted if the diameter is anywhere between 29.99 to 30.01. If the diameter of the shaft is anywhere between 29.99 to 30.01, the shaft will be accepted. The diameter must lie within this range. Then he can choose an appropriate manufacturing process to realize the diameter. Why a dot dimension cannot be manufactured? 2 reasons I have cited. One is it doesn't exist. There is nothing called exactly 30 mm diameter. Number 2, a production manager doesn't know I am inaccurate in my statement. When I say the diameter is 30 mm, I am inaccurate in my statement. When my statement is not accurate, it cannot be realized, it cannot be verified. Later on somebody wants to check. A production engineer has manufactured. But later on somebody wants to check whether he has manufactured as per the drawing. If you say 30 mm diameter, it doesn't exist, then how can he check whether 30 mm is that? Now I don't know whether I am making you or able to appreciate what we are talking about. Okay, so even for checking, I must specify a tolerance band. Okay. Now this is one aspect that I want you to understand. Now let us take another situation. Can you go to the next slide, please? Now why should I specify indicator tolerance? Okay, this is a rough image that I have taken. I don't know where exactly this part is being used, but I'm imagining this to be a bush shaft. I'm imagining this to be a bush shaft. Now what is the purpose? I have a shaft which needs to be supported. The shaft is a rotating member. The shaft needs to be supported. So in between, this is the housing in which the shaft is supported. So this is a push. You can see it in many places. A bush shaft is something similar to a bearing. Bearing, I would have told, there is something called a rolling contact bearing. There is something called a... Yes, somebody said it? Sliding contact bearing. Very good. I am very happy you remember that. A bush is a sliding contact bearing. Okay. Generally, this part is made up of some anti-friction material, bronze or... You would have studied. Are you familiar with this? Are you doing plumber block or they doing in the AutoCAD? Plumber block? Footstep bearing? No. Okay, fine. Forget it. This is made up of some material like bronze, which offers low coefficient of friction. This is the housing. Okay, this is the shaft. Now, imagine, see, there is relative motion. The sliding actually takes place between the bush and the shaft. So the bush is made up of a frictionless material. So there is heavy amount of sliding. It rotates actually. So sliding takes place between the bush and the shaft, and the shaft remains firmly attached to this. So there is no relative motion between. There is no relative motion between the housing and the bush. Am I clear? The relative motion between housing and the bush is undesired. It is not required. The relative motion between the housing and the bush is not required. Okay. What you require, it is in fact, it has a negative effect. On the other hand, what you require is the relative motion between the shaft and the bush. Now, how do you achieve this? Is it like when Caesar says stop, something stops? Is it something like that? No. I want, at a particular joint, I want a relative motion. I want the relative motion to be permitted. And at some other joint, I don't want any relative motion. Now I can achieve this in many ways. Now are you able to appreciate the problem? I don't want any relative motion between the bush and the housing. But I want a free running between the shaft and the bush. My question is, how does that happen? If the designer say, okay, let that be free running fit, will that be free running? Or if the designer says, no, there shall be no relative motion, will the relative motion cease? How to achieve this? Are you able to understand the problem before us? Is it clear? Is the problem clear? At one particular interface, I want free running taking place. At some other interface, I don't want any relative motion. How do I realize this? Any suggestion? A very simple mechanical component. Only there are three parts. One is the shaft, the third one is the bush. I mean, the second one is the bush, the third one is the housing. Is it okay? Now let me make the drawing because we will be spending some time in this. Okay, the three components are: you have a shaft, say the length is say 50 mm, the diameter is say 16 mm. Then you have a house, you have a bush. Here also we will usually provide chamfer. Here also we usually provide a chamfer. Are you able to understand the diagram? Then you have a housing. Then you have a housing. Okay. Now say this can be taken as say 18 mm. Okay, this diameter can be taken as 32 mm. So naturally this diameter is 32. This diameter is say 60. Is it okay? This diameter obviously is 60. Is the system clear? So the 16 mm shaft is this, and I am talking about this part alone. These details I have not bothered. The bush drawing I have given, the housing drawing I have given. Now my problem is, in between this 16 shaft and the 16 hole, it must rotate freely. Then only the shaft will rotate. On the other hand, between these 32 mm diameters, there should not be any relative motion. Now, how am I going to realize this? This is the essence of the fits and tolerances that we are going to discuss. Any ideas? Please think.
Degrees of freedom in permit free motion.
Good thinking, but how to do that? Don't give me concepts. Tell me exactly this is how you have to do it.
The housing and the bush are kept in contact with each other, whereas the shaft and the bush are given some amount of little space.
Beautiful, beautiful. What you do is you provide a small space. Let me use his words. in between the shaft and the bush. But let there be no space. That's what he wanted to say, between the bush and the house. Or let me put it in again in colloquial terms. Let there be no gap at all. Let the bush and the housing, let it be very tight. Is it okay? Let this and this be joined in such a way that it is very tight. I am not using any engineering terms now. At the same time, let the shaft and the bush, let them be connected with some gap. Now let me use the corresponding technical terms. Let there be some clearance between. Let there be some clearance between the shaft and the bush. And let there be some interference. At certain junctions, we want the two bodies to rotate very freely. At certain other junctions, we say there should not be any relative motion. How to achieve this? Now let me first say it very crudely, then probably we will refine. So here the 16 mm diameter, okay, make it as 16 plus 0.00 minus point. Let me not with 16 mm, the shaft 16 mm. This is the dimension. Now, for the bush, the 16 mm, I just make it plus 0.1 minus 0. Now let us analyze the situation. What happens? See, the diameter of the bush, the internal diameter of the bush can be anything in between 16 to 16.01. So the whole dimension is not permitted to become smaller. The whole is permitted to become bigger, larger. Better talk. Okay, the whole is permitted to become larger. On the other hand, the shaft is not permitted to become larger. The shaft is only permitted to become smaller. When I make the dimension like this, that is the meaning of it. When I take a shaft and then pull and assemble, there will always be a gap between the shaft and the hole. In the gap, you can put some oil, some lubricating oil, which will induce hydrodynamic lubrication, as you will study later. There will always be a gap, so it can run very freely. The shaft can run very freely in the bush. Accepted? Are you able to understand? Now this shaft can run very freely inside the bush, because by controlling the dimensions, that is the beauty of it. As a design engineer, by controlling the dimensions, I have made the shaft diameter slightly smaller, I have made the hole diameter slightly larger, and ensured that there is always gap between the shaft and the hole. This gap will subsequently be filled with some lubricating oil. The shaft will be able to run very freely inside the bush. Now, coming to this 32 mm diameter. Now this 32 mm diameter of the bush, what I am going to do is, I am going to make what sort of relation is one between these two? No relative motion. As he said, no gap. So what I am going to do is, this 32 mm, I am going to make it plus 0.1 minus 0. So here, the outside diameter of the bush is going to be larger. And what happens to the hole? In the housing, I make this diameter the whole diameter slightly smaller. So the hole will always be smaller than the shaft. The housing diameter will always be smaller than the bush outer diameter. When you assemble them, I may have difficulty in assembling. I may have to hit it and then push it inside. But when assembled, there won't be any relative motion between. So by simply controlling dimensions, I am able to achieve whatever I want. If I want free running, I can have free running. If I want no relative motion, I can achieve no relative motion. All that I need to do is, I need to control the tolerance I give on each and every part. I need to control the tolerance I give on the part. By just controlling that, I am able to realize any type of relative motion. Now let's take the question, why fits and tolerances? The reasons are twofold. Why should I give a tolerance? The reason is twofold. I should give a tolerance because the dot dimension, it doesn't exist. The exact dimension, it doesn't exist. It doesn't exist. It is not possible to manufacture to an exact dimension. It is not possible to check an exact dimension. This is number one. Number two, by controlling fits and tolerances, I can achieve any type of relative motion I want between two components in time. If you want interference, you can achieve interference. Interference means what happens? What happens in this case? In this case, the material of the shaft, here the material of the bush. Okay, any outside feature is called a shaft. Any inside feature is called a hole. See, earlier, if I refer to this hole and this shaft, this is the hole and this is the shaft. When I refer to external dimension of the bush and then the hole of the housing, this becomes the shaft feature. This becomes a hole feature. Any outside diameter is referred to as a shaft feature, and any inside diameter is referred to as the hole feature. Now, coming to the bush, the outside diameter of the bush is going to be slightly larger than the inside diameter of the housing. So what is the effect? The material of the bush and the material of the housing, they are going to interfere. There are many ways to achieve this interference. So simplest way is, you suppose you heat the hole, you heat this entire housing. What will happen? It will expand. It will expand. Then you insert the bush. Insert the bush and allow it to cool. What will happen? It will contract and there will be interference between the housing and the. See, one classic example, because aero students are also here. One classic example that comes to my mind is the skin of the aircraft is riveted to the structure. It's all known to you. Okay, that's why you study about riveting so much. Okay, aero students study about riveting a lot. Okay, because the skin riveting is a very important metal joining process for aero students. Now my simple question is, aircraft must be airtight, obviously. Okay, when I rivet something, you have a plate, you have a structure, say you have an eye section, you have a very thin plate, these two are to be joined together by means of riveting. How do I rivet it? You first make a hole, it will become something like this. Now how will you want the hole to be slightly, for easily assembling the rivet, the hole must be slightly larger than the rivet diameter, is it not? So here there will be some gap. How will you achieve anti-this? And please believe me, this is not one rivet. There are going to be hundreds of thousands of rivets all over the aircraft. How do I ensure airtightness here? The simple procedure is, what you do is, you drill the rivet, drill the rivet hole. All the rivets are kept in liquid nitrogen. They are made up of aluminium alloy. All these rivets are kept in liquid nitrogen. I cannot heat the aircraft. Aircraft is so huge. I cannot be heating that. But on the other hand, what I can do is I can cool the rivet. So I take the rivet out of liquid nitrogen and then put it into the hole. It will very easily go into the hole because it is shrunk. The diameter is smaller. So as it is taken out of liquid nitrogen, it will be very soft. I can very easily deform and form the hole. I can leave it. What will happen? The rivet will slowly expand and close the gap. You have achieved both. You are able to easily put the rivet and you are achieving something more. The rivet material, it will undergo what is known as it is brought to room temperature, it will undergo a process called age hardening. We will study about it later. The aluminium, it is an aluminium alloy, it undergoes age hardening or precipitation hardening, and after some time it will become very hard, very strong. During riveting, I don't want it to be strong because I have to apply extra force if it is very strong. During riveting, it is very soft. But after some time, what happens? It age hardens. Age hardening. It undergoes a process called age hardening or precipitation hardening. It becomes strong. I have achieved two things. One thing is airtightness. Another thing is age hardening. So this is done in aircraft riveting. So again, an interference fit. So interference fit can be attained. This is called a shrink fit. When you heat it and then apply an interference fit, it is called a shrink fit because you make it shrink and then the fit is uptight. Or I can get a dry fit. What is a dry fit? You hit it, drive it hard. You drive it inside. It is called a dry fit. So there are many types of interference fits. Similarly, there are many types of clearance fits. A clearance fit is something in which you have a clear gap. There are many types of clearance fits. There are many types of interference fits. Okay. There are a group of fits in between. Okay. There are a group of fits in between. We'll see briefly about all this and then we'll go to the next agenda called robustness. Next slide please. Now you have a hole. What is shown in crossed lines is the tolerance on the shaft. What is shown as crossed line here, this is the tolerance permitted on the shaft. This is the tolerance permitted on the hole. Okay. Now what type of fit will you get if you have such a shaft and such a hole? It will be a clearance fit. Is it okay? So obviously you will get a clearance. Oh, next slide please. Now these are the recommended fits. These are all available in a data book which we'll be using as design engineers. We have a standard data book called PhD design data book. Aero students, mechanical students, all of you will be using this data book. I just scanned from that. Okay. So if you want to have a running fit, like between the shaft and the bush, you can choose any one of the fits in this region. So this is a running and sliding fit. Next slide please. locational and assembly fits. I just want to locate two parts, or I just want to assemble two parts. So here I don't want too much of interference, neither I want too much of clearance. If there is too much of clearance, there will be inaccuracy in locating. So that is the next case, locational and assembly fit. Next, transition and interference fit. Transition is in between clearance and interference. So you can have an interference fit. See, this is the hole. This is the hole dimension. This is the tolerance of the hole. This is the tolerance of the shaft. If the shaft diameter is so much, you will definitely have interference. If the shaft diameter is this, you might have interference. It depends on the hole diameter. So this is a transition fit. Next slide, please. So these are the recommended fits for transition. Next, these are the recommended fits for transition and interference. Next slide, please. Next, go back. Here, now I have to. Now I can specify the tolerance on the shaft as well as the tolerance on the hole. Believe me, making a hole is much more difficult than making a shaft. In engineering, you will realize it when you manufacture components, when you design components. Because when you are working on the shaft, you are working on something external, outside. That feature is external. The diameter is outside. You can easily access it, you can easily work on it. On the other hand, if you want to make something on a hole is an internal feature. Simple example is, can you do turning on a shaft? You can do it? Yes or no? Can you make an internal hole on the shaft? Drilling is fine. But more than that, can you do boring? Boring is much more difficult. Any process done internally is difficult. Okay, like if I have a wound here, it is easy for me to cure. But if I have a small ulcer in my intestine, it is very difficult for me to heal it. Believe me, like a small cut in my hand, which I may not bother to even treat, or I may just put some antiseptic here, it will get cured. If a very similar cut is there in my intestine, inside my intestine, it is very difficult to access it. I have to undergo an endoscopic procedure, apply the medicine there. Even to apply the medicine, it is very difficult. Because it is an internal organ. And even in the internal organ, it is inside the intestine. There are two things. It is an internal organ. Even in the intestine, anything outside can be treated easily. Probably I can cut open and then even treat it. If in the outer wall of the intestine there is some problem, I can even cut open and then treat it. But the inside wall of an intestine is much more difficult. I don't know whether you appreciate the complexity involved. Okay, intestine is inside my stomach, but the internal wall of the intestine is still not reachable. So, any internal feature is difficult to make, difficult to control. So, we evolve what is known as a hole-based system. We go for what is known as a hole-based system. What is a hole-based system? What I do is, the tolerance on the hole will always belong to what I call as a H category. The tolerance on the hole will always belong to a H category. Typically H7. H7. most of the holes, 99% of the holes will have the tolerance H7. Why H7? Because if you just drill a hole and perform a manufacturing process called reaming, there is a manufacturing process called reaming which can be done in the drilling machine itself, I will be able to realize a H7 tolerance. So what I do is, I get whatever fit I want by controlling the shaft dimensions. By varying the shaft dimensions, I will be able to get whatever fit I want. So most of the holes will have the H7 tolerance and the shaft dimensions are accordingly controlled. Can you go back please? Suppose I want go back please. Go back. Go back. Go back. Yes. Now, suppose I want a normal running here in between the shaft and this bush. What do you want? I want a normal running. Okay, it should freely rotate within the bush. So what I do is, I select a H7E8. Here you have H7E7. So I select H7E7. So this capital letter, it stands for the whole feature. The small letter stands for the shaft feature. So based on the type of fit you want, you choose a particular tolerance pair. This is called a tolerance pair. H7E7 is called the tolerance pair. How do I select it? I want a normal running. In what situations it is used? It is described here. Used for properly lubricated bearings with appreciable clearance. Finer grades for high speeds and heavy loads. Turbo generator. Large electric motor bearings. So these are the applications. I want a free running between the shaft and the bush. I choose this particular tolerance pair. H7E7. Now what is the meaning of this? This capital letter, it stands for whole feature. Not because H is whole, no. Capital letter stands for whole feature and small letter stands for the shaft feature. Now let us go forward. Table is ready. Please go to the table. Yes. Next. Shaft is ready. Next. Back. Yes. Now you can see H7 is given here. Capital H7 is given here. Are you able to see? What is the diameter of the shaft? The diameter of the shaft is 16 mm. So for H7 16 mm, the diameter is given on the top. H7 16 mm, the tolerance is given here. So the tolerance on the hole is plus 00 plus 18. So the whole dimension is, here I should write 16 within bracket H7. And what is this? H7 16. Sir, can you please mark it for me? H7 16 is plus 18 plus 0. So plus 0.018 plus 0.007. This is the whole dimension. So the whole will have a tolerance of 16 mm H7, meaning the diameter can be between 16 plus 000 plus 0.018. Is it okay? Now coming to the shaft. Shaft is E7. Can you please go back, sir? We'll get E7. E7. E7 is here. E7 is here. And if you come to 16, minus 32, minus 15. So the shaft diameter is diameter 16 E7 minus 0.0. How much? 32. Minus 32 minus 50. Minus 32 minus 50. So the tolerance span is H7, E7. The capital letter stands for the whole feature. The small letter stands for the shaft feature. So I have obtained the required tolerance for free running. Now shall we do a similar exercise for the 32 mm diameter between the bush and the housing? What do you want to achieve? Between the bush and the housing, should there be free running or what type of fit you want? Tight fit. So can you use a technical term for that? An interference fit. An interference fit. Can you go back? Okay. Interference fit. Go back. Next. 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 Right. So in the interference fit, I have to now decide how I want my interference. Is it just good enough if I just press it with some force? That is called a press fit. Then drive fit. It is more of force. You understand? I have to drive it. Still heavier driving. Then what is the next one? Force or shrink fit. Next. Go back. So is it just press fit? Is it drive fit? Okay. Or is it heavy drive fit? Or force fit for or interference fit? What shall I choose? I shall choose the second drive fit. Okay, I don't want to. I cannot be heating and then shrinking. That is not possible for me. Okay. So I choose. Okay. H7 S6. H7 S6. H7 stands for what? Hole feature. S6 is going to be for the. Where is my hole here? Here. 32 within bracket H7. Now how will you determine what is the tolerance? Tight fit. No. What is the exact values for H7? 32 diameter. I should go back to the table. Next. Right. H7 and 32, 30 to 40. H7 is plus 25 plus 0. The dimensions given are in micron. Plus 0.025, 0.006. Okay? Plus 25 plus 50. So this is for the whole feature. Coming to the shaft, it is S6, small S6. Can we see small S6? That is S6, 32 mm diameter. Next, it is plus 59, plus 43, plus 59, plus 43, plus 59, plus 43 is S6. You can see that the whole dimension is smaller than the shaft dimension in all cases. So I have to just cross it. Are you able to understand? So this completes. I have just given a very brief introduction of Unfortunately, you don't have any paper in which you will be studying geometric tolerancing in detail. So this is a sort of introduction about how the dimensions can be controlled to obtain the required fit. Any doubts you have? What do you use a hole based system? Why do you use a hole based system? It is, what do you mean? What do you mean by a hole based system? What do you understand by the term hole based system? The tolerance on the hole is always the tolerance on the hole is always H7, H6 or H8. It is all the tolerance band on the hole is fixed. Only by changing the tolerance band on the shaft, I obtain different fits. This is called the hole based. Are you able to understand or not? You freeze the tolerance band on the hole. It is always H7 or H6 or H8. These are the only three variations possible. No other ABCD. The hole will always have H. So in 99.99 cases, you will be using only hole based systems. Okay, the tolerance of the hole is frozen. Then how will you get the required fit? By changing the tolerance of the shaft. See, for example, in both the cases, the hole dimensions are H7. Here also H7. Okay. Here also H7. Here also H7. But here, what type of fit you get? Free running fit you get. Here, what type of fit you get? Interference fit you get. How do you achieve that? By changing the tolerance of the shaft. So this is what we mean by a hole based system. Why do we go for a hole based system? It is difficult to control a hole rather than a shaft. That is why we go for a hole based system. Is it okay? Any doubts you have? Now, the next. Okay. I'll briefly, for another 10 minutes, I'll explain the idea of robust design and then we will call it a day. Okay. Now, you design a system. But what is inevitable in nature is, in nature everything keeps varying. People say the only permanent thing in life is change. Things always keep changing. Nothing remains stationary. The only permanent thing that you can think of in life is change. Things keep on changing. Variation is the essence of nature. When you design a system, you design a system assuming certain conditions. But what happens is, you have designed a system, but many things keep changing. Change from what you have assumed to be in your design stage. Now let me take up an example. Let me take up a very concrete example. I mean, the idea of robust design was put forth by Taguchi. Let me take up the problem that he encountered originally and then let us try to learn what robust design is. The problem before Taguchi at that time, this happened sometime in early 1930s and 40s, or rather 1950s. He was looking after a brick manufacturing facility. Taguchi was looking after a brick manufacturing facility. So they were making, as you all know, bricks. They mix clay with sand and then they make it to the required shapes. They dry it. After that, what do? They put it in a furnace called the kiln and then they heat it. In the furnace, the temperature is raised to below certain temperature and then you get a very strong ceramic formation takes place. You get a brick. Brick is essentially a ceramic. The bond between the granules, it is strengthened and thereby you get a ceramic. Okay. So brick is essentially a ceramic. And the major problem for Taguchi was certain bricks are getting overburned and certain bricks are getting underburned. If it is overburned, the appearance will be bad. It may not be very strong. Okay, it will be blackish. It has to be rejected. When it is underburned, the ceramic formation would have been incomplete. Again, these parts are to be rejected. Now, what is the problem? The problem is underburning and overburning of bricks. Now, what is the solution? Why underburning and overburning? I mean, underburning of bricks or overburning of bricks takes place. Why does it happen? Can you put yourself in that situation and then analyze why underburning must happen at all? Everything is put inside the same furnace. Why should there be underburning at certain parts?
It's not uniformly exposed.
Fine. The temperature distribution within the furnace is not uniform. Temperature is not same at every point. You know that ceramic formation takes place at a particular temperature, but inside the furnace, the temperature distribution is not uniform. If the temperature is low, you have underburning taking place. If the temperature is high, you have overburning taking place. Not big engineering, is it not? So, how to eliminate underburning and overburning? Yes. To have, if you ensure uniform temperature distribution, the problem is solved. If you provide uniform heating throughout the furnace, the problem is solved. So what is the solution? What should the person do? To provide uniform distribution of temperature inside a furnace, what should I do? Okay. Let us redesign the furnace in such a way that you provide fans, you control the flow of air inside the furnace so that the temperature distribution is more uniform. Got it? I have to redesign the entire furnace in such a way that there is a uniform temperature distribution within the furnace. Then the problem is completely solved. If the temperature distribution is uniform inside the furnace, okay, there is no overburning or underburning of bricks, the problem is solved. But the question Taguchi took up was, see, the alternative is, if I have to redesign the entire furnace, it is a very expensive process. I have to throw away the existing furnace, redesign, remanufacture and install something in place. It is a very expensive proposition. So, what Taguchi asked himself was, of course, he had identified successfully the root cause of the problem. What is the root cause of the problem? The root cause of the problem is non-uniform temperature distribution. How to eradicate the root cause of the problem? Redesign a furnace with uniform temperature distribution. The problem remains solved. But what Taguchi asked himself was, I can I can resort to this solution, but this is an expensive solution. You can redesign and refabricate the entire furnace, but it is a costly process. Can I modify the brick making process in such a way that even if the temperature variation exists, the bricks produced will be uniformly formed? The question that he took up was, can I modify the composition of clay and sand and other things? Can I play with that? Or can I play with the process of manufacturing bricks in such a way that I make the brick manufacturing process more robust to temperature variation? Why should it be so sensitive? Even if there is a slight change in temperature, why should it be underburnt or overburnt? Why don't the whole process be more robust so that the variation in temperature will be there, but still I'll be getting good bricks? What is the logic? The logic is, if I design my process in a robust fashion, the whole problem can be solved in an easier fashion, in a cheaper fashion, rather than resorting to expensive solutions. The question is, you have done a design. Is your design robust, or is it very fragile? Is it very sensitive? You have designed a system. Fine, it is a very good design. But if the system is very, very fragile, if the system is very, very sensitive, it has to be very closely controlled, then it is going to be very, very expensive. So when you design a system, you should design it in such a way that the system is robust. The basic contribution of Taguchi is, whenever you have a problem, what is the traditional approach? The traditional approach to solve the problem is, whenever you have a problem, you identify the root cause, attack the root cause, solve the root cause. You have a problem, what is the root cause of the problem? You solve that. That is the traditional problem solving approach. Taguchi begged to differ. He wanted to resort a different approach. What is the different approach? Of course, solving the root cause of the problem is that. But that is an expensive route. Can I assume that the root cause will remain? The root cause of the problem will remain. But still, make my design more robust so that it is insensitive to these process variations. So if you could design a system like this, that is called a robust design. So what is a robust design? A robust design is a one which assumes variability. In any existing system, robust design assumes variability. It assumes that things are going to go beyond control, but still, will my system remain safe? Will my design be robust so that it takes care of all these variations? Of course, there are many aspects of robust design. Based on the idea of robust design, Taguchi evolved a very, very useful experimental technique called factorial design, which basically helped him to identify the level of influence of each parameter on the performance. You have 10 parameters. How these 10 parameters influence the performance? You need to study that if you want to make your system more robust. So he has developed a concept called design of experiments, and this is a separate domain of study by itself. Now all that I want to impress upon you is, you have designed a product, You have given dimensional tolerances to it. You ensure that the whole process, the whole design is also robust. Now, let me take another 5 minutes or 10 minutes to summarize what we have seen in this course. Okay. And then we will call it a day. Now, we have two objectives in this course. One is to introduce the design process. Why should we learn about the design process? Because design is the central activity in mechanical. Design is the creative activity in mechanical. That is the place where a product takes its birth. So, we wanted to understand the entire design process. So, where does the design process starts? It starts from a need. So, we have studied the voice of the customer, how to collect the voice of the customer, how to process the voice of the customer, how to convert the voice of the customer into technical specification. So technical specification is only a target, is some defined goal that is to be achieved in the design process. Then to achieve the technical specifications, we do a lot of other things like benchmarking, product teardown. Then we generate concepts to reach the technical specifications. Before generating concepts, the technical specifications are to be functionally mapped. So we have extensively studied about functional mapping. What are the various functions and sub-functions to be performed by a product? And we have studied the black box method of representing the functional mapping. And we have studied two methods of detailed functional mapping called FAST and the comprehensive functional representation schemes. Now, later on, we have taken each function separately and then we try to generate concepts to attack these functional specifications. We generated various concepts, we have evaluated them, and then we have chosen a particular solution. Then comes the implementation, the embodiment design phase, wherein we have converted a concept into, we have given a body to the concept. Concept is only an idea. In the embodiment design, we have given a body to the concept, and the output of the embodiment design is the detailed design of the product in the form of drawing or model. It can be a three-dimensional model. Then we have seen the role of modeling in the whole scheme of things. And later on we have concluded by studying about dimensional geometric tolerance, particularly dimensional tolerancing and robust design. Is it okay? Anything that you would like to discuss? Now in the test evaluation, I find certain things like you have not understood the idea of modularity. Okay. Even people have attempted big questions on modularity, but still, I could very clearly see that they have memorized and then reproduced something. Okay. What do you mean by something being modular? Let me give a very, very simple example, because this is a very important idea. I find something missing. Probably I have not explained clearly. What do you mean by a modular design? Suppose you have your, there is some problem in the hardware of your computer. Okay, you take it to a service person. What does he do? He will say, sir, there is a problem in the motherboard. The motherboard needs to be replaced. Okay. Or he will say, sir, there is some problem in the VGA part. The VGA part needs to be replaced. Now, does he ever tell you what is wrong with the motherboard? Which chip in the motherboard has gone wrong? Why? The motherboard is taken as the basic module. Do you understand? Then the motherboard can be divided into many sub-modules that generally they don't do before you. Suppose you take your laptop, he may say some 5-6 problems. Sir, the keypad is the problem, the keypad needs to be replaced. The display unit is a problem, the display unit needs to be replaced. The motherboard is the problem, motherboard needs to be replaced. The power card portion is the problem, the power input module needs to be replaced. So the whole product is divided into some 5-6 modules, and servicing is done only at this module level. But we are not looking at the problem at the service level. We are looking at the problem at, I gave this example only for you to understand. We are dealing with the problem at a design level. You design in a modular fashion. Let us take the example of a software. Okay, you have to design a software to solve a particular problem. Okay, for writing numbers in an ascending order, you write a module and keep it ready. For solving simultaneous equations, you write a module and keep it ready. Okay, for performing numerical integration, you write a module and keep it ready. Put all these modules depending on the need. Don't go and write all the solutions for a particular software problem. This is a modular approach in software design. In product design also, you approach the problem in a modular fashion. That is, the total problem is divided into many modules and each module is taken up for design, and we explore the possibility whether the product portfolio can be enhanced by just changing certain modules. For example, in a car, the engine module can remain almost same for 3-4 modules. We can still make changes and we can still make them look different. The engine module can be different. Or the fuel intake module can remain same. Whatever is the engine, the way the fuel is intake and then delivered to the engine, that module can remain same. So this is the advantage of modularity in design. Is it okay? Any doubts you have regarding the entire process? Okay, in which case I wish you all the best in the forthcoming examinations. Do study well. Go through your textbook. I re-emphasize again, because that will give you a lot of opportunity to learn more than what is being taught in the class. Okay, don't just rely on the PowerPoint presentations. I don't mind giving it to them. Of course, you have been getting that. Okay, you have been getting the PowerPoint presentations, but don't just rely on that. Go to the textbook and then learn more. Is it okay? All the best in the forthcoming examination. I have a small feedback form. Okay, all of you can receive the form and then take 5 minutes, take it seriously. Okay, spend 5 minutes on it, take it seriously, and then fill up the feedback form and hand it over to us. Okay, there is a last column in which you can write your GPA if you want. It is not to trace back. You need not write your name or anything in the feedback form. Your number, name need not be written. But we want to ascertain how different sections of students react to the issues. Okay, so it is optional. If you want, you can give your GPA. Is it okay? All the best. Good day.